Thanks everybody for joining today. This is the third session of the series we have started last month to talk about different Azure Cloud patterns. And today we are going to cover four main patterns: asynchronous request reply and ClaimCheck, external configuration store, and Cacheaside pattern. So the first pattern we are going to talk about is the asynchronous request reply pattern, and it comes under messaging category of cloud design patterns, because as we are going to see, it's primarily working on message queues and these kind of things. And we have talked before in a previous session about using the publisher subscriber pattern or pub/sub pattern to decouple the communication between a producer and subscriber. And then, but the thing about this pattern, it was one-way communication. And this pattern, asynchronous request reply, is trying to do the same, decoupling the backend from the front end, so the backend can spend as much time it requires to finish the backend processing, and then it will be able to notify the front end asynchronously when it finishes the execution of the backend process. Let's assume that we have a group of users using Chrome browser, and we have also an API in our system, and then the Chrome browser is going to interact with the API to get some data, and then the API is going to respond back to the Chrome browser or to the client application with the data that they are asked for. So far, it's going to be a real-time request response fashion between Chrome browser and the API. Generally speaking, there are different standards of how quick the API request or response should be ready. Many organizations have different standards. Some organizations have 10 milliseconds response as a standard. Other organizations have 100 milliseconds. Whatever the standard is, it has to be returned really quick, as long as we are dealing with a real-time request response. Also, there are different factors we need to be aware of. The geographical location of the user, in which the Chrome browser, it might be in a different geographical region from the API or the location where we hosted our API, and it might have an additional latency for these different requests response. Also, the time that's going to be required from the API to take to prepare or to finish a certain request. Also, what data might be transferred between the client and the API, and these different things. So this is the way if we are going to plan, like if our API is going to respond within milliseconds, definitely we need to go for real-time request response. But in some scenarios, these APIs might take seconds or even minutes or sometimes hours to finish a long-running process. And in this case, we cannot letting the client hanging around waiting for the processing or the execution to be ready. So what we are going to do in this case is to introduce an Azure Service Bus. So the client application, the Chrome application. Can I ask everybody please to put their mic on mute? Thank you. So the Chrome in this case is going to send or publish the messages to the message queue. And then from the other side, the API is going to pull the messages from the message queue to start the execution of these messages. Then we have done the one way or one part of the communication, which is from the publisher or requester, which is the Chrome application, to the API. Now, when the API wants to send the data back to the Chrome application, how can the API send a synchronous response to the Chrome application? This is exactly the challenge that we have in here. And this is how the asynchronous request reply pattern is going to help us to improve or solve this problem. And to understand how can we implement it, let's look at this diagram. So what's going to happen is that the client is going to send a request to the API endpoint. And then once our API endpoint kicked off or started the execution of the backend long-running process, it's going to send back to the client HTTP 202 accepted response code. This is an acknowledgement that the API has received the request and started the execution. We need to be aware of that when we're sending 202 response code, that we need to perform the validation at the API endpoint before sending the 202 response code. Because if the client sent an invalid input to the API endpoint, we want to let them know as soon as possible. All right. If the client sent an invalid request or invalid data to the API endpoint, we want the client to know as soon as possible. There is no point for keeping the client hanging around for a few minutes or even hours and then tell them, oops, you've sent something wrong. You need to send it again. And what we need to do from the API endpoint is to validate the input or request that the client has sent. And if everything is perfect, then we are going to respond back with 202 response code. Also in this response, we want to send the client the location and the frequency where they can find the status endpoint and find the final resource that they are requested. And then as long as the client is going to send the different requests to the status endpoint, it's going to send the 202 response code, like we are telling the client, yes, we have got this request already and we are working on it. Until the processing of the backend process has been completed. This is only the status endpoint is going to respond back with 302 HTTP response code, which is then tells the client or redirects the client to grab the actual resources that they have requested. And then in this case, we are going to send the client 200 response code, which is okay. So this is how can we implement the asynchronous request response and how we can manage the communication between the client and API endpoint and status endpoint until we finish the execution of the backend or a long-running process. Now let's look at how we can implement this in Azure. Same thinking, like assuming that we have the client application, Chrome is going to send a request to the API, which is hosted in Azure Function App. And after it performs the required validation, it's going to put the message in a message queue and then respond back to the client with the status endpoint. Then from the other side, when we place a message in the message queue, it's going to trigger an execution for another function app, which is going to pull this message from the message queue and perform the long-running process. Also, you need to be aware of the Azure Function App limits in here. If you are expected that this long-running process is going to exceed the limits of the Azure Function App, then you might need to use the durable function because it has more validity than the function app. Anyway, and then this second function app is going to perform the long-running process and then put the result in a blob storage. And then we have a third function app, which is exactly the status endpoint that the client is going to call every now and then. So to check if the result is ready in the blob storage, so the client can grab these results or not yet. So this is how can we use Azure components to implement this pattern. And definitely you can replace the function app and use app service or any other serverless component. You can change the message queue and use topics or event hub. And also you can use any other cloud-based storage other than blob storage if you would like. Now let's look at some considerations we need to be aware of when we implement this pattern. Talking about the pure REST semantics. If the resource is not available, we should respond back with 404 response code because the resource is not ready. But what we have implemented in here that we are working on this response or generating this output that the client has requested. Then we have responded with something a little bit different than the pure REST semantics. So you need to be aware of that deviation that you are doing in order just not to confuse the client by applying the pure REST semantics. Because if we responded with 404 while we are working on the backend to prepare the output, the client is getting confused. What does this really mean? He received 404, which means that the resource is not ready, but at the same time we are working on it. And maybe after a few seconds, he receives another request that the resource is now ready for access, which is going to be confusing for the client. And as I said, when we send the 202 response code, we need to put the location and the frequency or retry after headers in the response. So the user can know the location where they can go to grab the resource when it's ready or the output when it's ready, and also retry after certain number of seconds or minutes. This is to avoid the client from sending overwhelming number of requests to the status endpoints. Sometimes you might need to use a proxy or facade to add additional headers or remove headers to these request or response. Also, you want to make sure that you are using the right HTTP request or response code. If you are going to redirect, make sure that you're using 302 or 303 response codes. If the request has been succeeded, you want to make sure that you responded back with 200 or 201 or 204 if there is no content. And if there is any error, you need to respond back with the proper 400 or 400 category of HTTP response codes. Some solutions are going to require using additional headers for these request and response, so you need to be flexible about this. And some legacy clients cannot support this pattern at all. And also you want to allow the client or give them an option to be able to cancel the long-running process that they have triggered already in a previous request. Now let's see when we should implement this pattern. When we have a browser, when it's difficult to have callback endpoints or use a long-running connection, it's going to add more complexity to your architecture. Also, when you have service calls that requires to use HTTP protocol and cannot trigger callbacks because of firewall restrictions on the client side. Also, when you have service call that doesn't support technologies like WebSockets or webhooks. Now let's see when we shouldn't implement this pattern. When you have a service built for asynchronous notification, like we can already use some of the built-in or already created services for asynchronous communication, like Azure Event Grid. You don't have to implement or reinvent the wheel and create something again from scratch. Also, when the response time must be immediate. We have mentioned already before, if the expected response time is going to be in milliseconds, you don't need to implement this pattern because it's going to add more complexity to your architecture. Also, when the client needs, we have a typo here. Also, when the client needs to return or collect multiple results and the latency must be minimal. Also, when there is a server-side persistent network communication like WebSockets, if you can use WebSockets, definitely you shouldn't use this pattern. Also, if the network design will allow you to use webhooks or have asynchronous callbacks. So this is everything we need to know about the asynchronous request response. I'm going to pause for a few minutes and take any question, either in the chat window or just unmute your mic and feel free to ask any question.
Hi, sorry I joined late, but according to this pattern, when we are hitting some of the function app and other stuff which are supported to the async call, are the Azure function and any other also support for whether the request is coming from the authenticated resource, or we can connect with the already plugin with the AD Azure AD so that the request can be authenticated?
Yeah, that's a good question. So, yep, we have focused primarily on the asynchronous request response. Other things that you definitely need to have the proper authentication and authorization. Definitely, it's going to be better if you have authentication been implemented through federated identity, through Azure Active Directory managed identities. And then definitely you have to use a proper Azure function key to make sure that the requester didn't request is authorized to call this function app. So yes, definitely all of these things has to be in place. We just focused on the core of the asynchronous request reply. In addition to like placing the function app in a certain VNet, if you want to limit it to a certain users. Also, if you want to apply access restriction policies for certain IPs or certain services to be able to call this function app. That's a good question. All right, let's move on to the next pattern. Next pattern we have is a ClaimCheck pattern. And again, it comes under messaging category. And primarily this pattern, when we receive a large message in a message queue, we are going to split it into two parts. The payload or the file, we are going to place it in a cloud-based storage like a blob storage. And then the ClaimCheck, which is the message itself that has a reference to this payload, it's going to be sent to the message queue. And there is a lot of benefits by doing this. We are going to see them in more details in a minute. Let's say that we have a publisher and subscriber, and we have decided to use an Azure Service Bus queue to integrate between both. So the publisher is going to send its messages to the Azure Service Bus queue, and then the subscriber from the other side is going to pull the messages from the message queue to process them. So far, we don't have any issue until the publisher decides to send a really large message to the message queue. Then we might have an issue. That this large message, it might take a lot of bandwidth from the message queue or from the subscriber, and it's going to be a bottleneck that might slow down the whole architecture. And even though this large message can be fits in the message queue limits, like there is a different limits for Azure Service Bus technologies. And some of these limits, if your message is beyond these limits, it's going to be an issue because the message cannot be placed in the message queue in this case, and it's going to be rejected from the publisher side. So being said so, let's have a quick look at the different size limits of the different Azure Service Bus components. So looking at Azure Storage Queues, it has maximum message size of 64 Ks, while Azure Service Bus Queues have a maximum message size between 256 Ks to 1 mega, based on your tier. Like standard tier, it's going to be 256 Ks, and the premium tier is going to be 1 mega. And then Azure Service Bus Topics, exactly the same as Azure Service Bus Queues. And finally, we have Azure Event Hub, which has maximum message size of 256 Ks. So bottom line is there is a limit, and the maximum limit we can go for is 1 mega. And in a scenario that we want, if the publisher wants to send a really large file like 5 mega or 10 mega to the message queue, it won't be possible. Then we want to think of something else so that will allow us to use this pattern or using a message queue to handle these large files or large payload as well. So what we can do is to introduce a blob storage or any other cloud-based storage. Then from the publisher side, we are going to split this large message into two parts. The payload, we are going to store it in the blob storage. And then once we get a reference to this payload, we are going to add it to the message that we're putting in the message queue. So when the subscriber receives this message, it will be able to pull the payload or the file from the blob storage because it already has a reference for this file in the message it receives. And by doing this, we have been able to overcome this message queue limitation by having as big as we want. We can have as many files as we can. We will not be restricted to this size limitation in Azure Service Bus anymore. Now let's talk about some considerations we need to be aware of when we use this pattern. Deletion strategy. You need to consider if you are going to delete the files or payloads you are placing in the blob storage, or you are going to archive them. If you are going to delete them, you need to think of if you are going to delete them synchronously, like the consumer, after it finishes processing on these files in the blob storage, it's going to delete these files. And definitely it's going to add a little bit of overhead on the consumer side. Or you might choose to delete these files asynchronously. And in this case, it won't add any overhead on the consumer side. Definitely storing or retrieving messages from blob storage, it's going to add more overhead and latencies. So you need to be very careful when you use it. It might be a good practice from the publisher side to check the size of the message before you place it in the message queue. And if the size of the message fits under these message queue limits, it might be a good idea to just place it in the queue straight away. Because yes, you might have a file required to be sent in a message, but this file is really small, like 1K or 2K. It will be more efficient and more easier for you, and even has less latency if you send this message or this small file in the message straight away to the message queue. And then from the publisher side, you are going to have this validation. So if you receive the file size that exceeds the limits of the Azure Service Bus queues or whatever messaging bus technology you are using, then you are going to split it and put it in a blob storage and put the reference in a message queue to put it in a message queue and move on. So this is just to avoid the additional overhead and latency that might come along if you're using this pattern. Now let's see when you should use this pattern. Whenever the message size cannot fit the maximum size limit of the service bus technology you are using. Also, when you want to ensure that the security is enforced, that only the publisher and subscriber and only two parties that are able to access these blob storage or the files in the blob storage. That's pretty much it for this pattern. Again, we're gonna pause for a few minutes to take any question.
So basically in this pattern, we are only putting the reference key on the message queue and the data will be on the blob storage, correct?
Yes, again, that based on how big the data is, probably you might, in a file upload scenario, you might have to upload certain files and want to link it with certain client ID or certain supporter ID in your system. So in the message, probably you can put client ID or all other information key value pair that you might want to send, but the actual file itself, which is the big chunk, you put it in the blob storage and put its reference in the message that's being sent.
So both the things need to be synced every time.
Sorry, what was that?
That is reference key and the actual data in
yes.
the blob.
Yes.
Okay, thanks.
No worries. All right, let's move on to the external configuration store pattern. So this pattern comes under design and implementation and operational excellence categories. And it's primarily trying to pull out the configuration information from the application deployment package and put it in an external central location. And there are a lot of benefits of doing this. Now, let's say that we have our application layer, maybe an Azure App Service or Azure Functions app, or even an old style application that's been deployed in a VM. Each of these application or components will have its own config file. Actually, it's not a file in case of Azure App Service or Functions app. It's primarily an area you can access it straight away from the Azure portal, access the configuration, and then you can put a lot of values in the configuration for the function app or app service. However, it's not the case for the VM. Anyway, now let's say that we want to deploy multiple instances of the app service. We know that all of these app services, additional app services, cannot access this config file because the config file cannot be shared across multiple app services. This is by design. And same thing might be we might have multiple or hundreds of function apps in our application, which are primarily using the same configuration, like using the same database connection string or username or password. So, and same thing, all of these function apps want to be able to access the configuration for one particular function app. And then similarly for the VMs, we might end up having each of the VMs has its own config files. Yes, for the VM, it might be a little bit different because technically you can allow network access to these different VMs or different apps in the other VMs to access certain config file in a certain VM, but it's not going to be ideal. So what we are going to end up with having a separate config file for each of these components. And if you have a really big application, you might have hundreds or even thousands of these config files. And imagine what would be the case if you wanted to change a configuration file. Maybe you wanted to change the database password or connection string. You'll have to go through them one by one in order to make sure that this config has been changed in all of these components. Not even that. After you change the configuration settings in the function app or app service, you have to restart the app service or function app in order for your configuration to take place, which is going to be a problem for you if you have a really high SLA that you need to maintain with your clients. So yes, technically speaking, restarting function app just take few seconds, but maybe restarting an app service might take longer than that. So bottom line is, it's not going to be efficient because we have to do a lot of changes in the same for all of the function apps or app services, in addition to the restarting time that's going to be taken for our changes to be effected. Now let's clean this up and see how we can use external configuration store to improve this situation. What we are going to do in here is to use a cloud-based storage, and we are going to pull out the configuration from the different components from the Azure App Service or Function App or on the VM, and put these configurations in a cloud-based storage. The cloud-based storage could be SQL database or blob storage or a key vault. So all of these different services, then it's gonna call or directly access the cloud-based storage to get its configuration data. And it's going to be way more efficient if we have hundreds of these components, like hundreds of function apps. All of them will be able to access the same config file in the cloud-based storage to get the data. And if we wanted to change the database connection string, for example, we can change it in one central location, and all of the other function apps or app services or VM apps are going to be able to read the updated data just by doing one change. And also, to make things more efficient, we can introduce a local cache. So all of these different components are going to read the data from the local cache instead of grabbing it from the cloud-based storage to make the retrieval of these configuration data even faster. And in some modules, some of these implementations prefer to have the local cache being stored in the application side itself. Like in the first run, the app service is going to grab the configuration data from the cloud-based storage and then place it in a local cache. And similarly for other services. But in this case, you will have to maintain a cache expiry period, like how long the cache needs to be refreshed from the base cloud-based storage, because you want to avoid having a stale data in the cache while the data has been updated in the cloud-based storage. So, however, these are different implementations you could use when you are using the external configuration store. And let's look at this diagram that explains what we have talked about. We have different sort of applications that are accessing the external configuration store, which could be stored in a cloud-based storage like blob storage or even a database. And then we have an option to store these configurations in a local cache as well. Now let's talk about some considerations about this pattern. As we are pulling out the configuration from different components or services in Azure and put it in a central location, we need to be aware of the performance and availability of this central location. We want to make sure that the blob storage or SQL or Key Vault will able to take many requests from different sources. And also we want to make sure it's highly available, because if this central location is not available, it's going to affect the availability of all of our services. And then the schema. You need to choose the external configuration store that supports multiple schemas. Most of the configuration data is key value pair, but sometimes you might have a complex data structure or complex data type that you want to store it in the configuration data as well. Also, you need to be aware of a hidden complexity you might have when you implement this pattern. Let's assume that your configuration file is stored in an XML file, and you have applied this pattern and placed the XML file in an external configuration store. Yes, technically you have applied this pattern, but in reality, when the application wants to pull certain information from the config file, it will have to parse all of the information in the XML config in order to get a certain value, which is going to add more complexity to your solution. Also, you need to be clear of the scope and have a clearance of the inheritance of these configuration stores. Like you might have some external configuration store that needs to be applied at the organization level. Some scopes needs to be applied at the application level. So you need to be clear what are the different scopes you're having in your organization, and whether you're allowing some of these configuration data to be overwritten, or you don't allow this at all. So for maths, it's very close to the schema we've talked about before. We want to avoid doing any data transformation because it's going to add a little bit more latency. So we want to make sure that our data store supports multiple formats as we want them. And if there is any error in the configuration store, or maybe the data doesn't exist, maybe it's a good idea to have a default value to return it either way to just avoid throwing an error to the client application, or also it will help us to perform some troubleshooting. Also, you want to make sure that only the applications that require access to the Key Vault or the external configuration store has access to it, and also limit it to the minimum least privilege access required. If the application is just required to do a read access from this config store, you don't want to provide them with the right access, right? And by having all of our configuration in one central location, we need to perform, when we change some of these config data, we need to test all of the applications that are referencing or using this config data, because we might have a single data in a config file or a config location that now being consumed by hundreds of applications. And if we're going to make some change, the testing scope should cover all of the applications that access this certain config data. And again, the cache expiration policy, as we have mentioned, we want to make sure that we want to avoid having a stale data in the cache while the real data has been changed in the external configuration store, but you still have a stale or all the data stored in the cache. Now let's see when we should use this pattern. When the configuration settings shared across multiple applications or services or instances of the same application. Also, when the standards, or when you have a complex data types like an image or complex data type that you want to store in your configuration settings, which are not supported by default in the normal configuration files. Also, you want to have these different scopes we have talked about before. You want to have different scopes in your organization and allow some applications to override certain configuration data. And definitely you want to simplify the administration effort if you want to change some configuration data across hundreds of these components. So that's it for the external cache, external configuration store pattern. And let's pause for a few minutes to take any question. All right, so let's move on. Now the last pattern we have is the Cacheaside pattern. And this one comes under data management and performance efficiency. Yes, definitely anything comes to caching will add more performance efficiency to your architecture. And this pattern is about loading data on demand from the data store to a cache. And while maintaining a consistency between the data that's stored in the data store and in the cache. We are not talking about the static data caching, like this kind of data that you load or you cache at the application start. We are talking about the non-static data that you need to cache in your system, which is a little bit different. Now, let's say that our application layer services could be Azure App Service or Functions App or Logic Apps or even API management. And we have a SQL database. This is our data store. And definitely all of the application layer services will have to communicate with the SQL data store to get or update certain values. And let's say this is the sample data that exists on the SQL data store. And let's say that we have a cache has been implemented somehow, and then we have cached the data for product ID 1, which is the same value that exists in the data store. Now let's say that we have updated the data in the data store and make the product name for product ID 1 is XYZ. Now the product name, it's gonna still AA in the cache because we don't have a mechanism yet to update or have this consistency between the data stored in the data store and the data stored in the cache. And this is exactly the challenge that this pattern is trying to solve. By the way, if you are using API management, there is internal caching available in the API management up to 50 mega, I guess. So yeah, if you are using the API management, you can leverage this internal caching before just going to the external one. Now, let's talk about some different caching strategies or operations that we might have in any system. We have read through, we have write through, we have write behind. So the read through means that the application or function app is going to check or read the value from the cache first. If it didn't find the value in the cache, it's gonna try to get the value from the data store and then put it in the cache for future use. Now for write-through operation, when we have an update process, the application is going to update the value in the cache. At the same time, it's going to update the value in the data store. It's going to add a little bit more latency, of course, but we are sure that the data are updated in the cache and in the SQL database at the same time. Finally, for the write behind operation, if we want to update some data, we update it in the cache. And then asynchronously, we update the data in the SQL by using a message queue to buffer these update requests from the application to the database. And based on your requirements, you can have an Azure function app that's been triggered for every single message being placed in the queue, so it can go ahead and update the data in the data store. However, if you are using this pattern, you need to be very careful that you are using a multi-cluster cache nodes, multi-node cache cluster, because if you are using just a single node and the data has been updated to this node and there is a failure happen to the single node that you have, then you are in trouble because you have lost the place where the data is updated, and in reality, the data hasn't been updated to the database yet, and you want to avoid to be in this situation. So multi-node cache cluster would be perfect if you are going to implement write behind operation. Now let's look at this diagram to see how can we implement these caching mechanisms. So first step, we are going to check the value in the cache. If we didn't find the value in the cache, then we are going to grab it from the data store and then store it in the cache for future use. As simple as that. Now let's look at this code snippets. I've got it from Microsoft documentation that explains it really well. So for the get operation, for example, we are going to check or grab the value from the cache, as we said. And if we get a cache miss, like the value doesn't exist in the cache, then we are going to grab the value from the data store. And then we perform null validation, and then we place the value in the cache for future use. And then for the update or write operation, what we are going to do is to update the data in the cache, in the data store. And then we are going to delete the data that are stored in the cache. This is to avoid us from reading a steal or all the data from the cache. So someone might ask, so how are we going to be able to read the new data again from the cache? And again, by going back to the read operation, when we find that the value is not existing in the cache, we are going to grab it from the data store. So we are going to get the new updated data from the data store, and then we are going to place it in the cache again for future use. So this is simply how we can use this pattern or Cacheaside pattern to have this consistency between the data store and the cache location. Some considerations we need to be aware of. Time to live, or TTL. You need to decide how long you want to keep the data in the cache. Is it 5 minutes? Is it a few hours? You want to keep a good balance between too short, too long, because if it's too short, you might end up having too many requests to the data store, and actually the caching wouldn't be helpful in this case. If the TTL is too long, probably the data might get changed in the data store and you are not getting notified. But this is not the case in here because we have already removing the data from the cache if it's been updated in the data store. Anyway, you need to keep a reasonable time to live for your cache. Not too short, not too long. Also, you need to think of evicting strategy or deleting strategy. Caching is different than the data store in its capacity. Caching is an in-memory data store, and in many cases, it might end up running out of space. And if that happens, you need to decide how you are going to delete the data from the cache. There are many strategies: first in, first out, last in, first out, or the least accessible data, or the oldest data that we have. Whatever strategy you are going to follow, just you need to make sure that you are aware of what deletion strategy you are using. Also, priming the cache. We have talked about already in some static data caching that some applications are loading those static data when the application starts up. And if this is the case, you need to consider how are you going to repopulate this data in the cache if this static data got deleted by the evicting strategies. You definitely want to avoid that you need to restart the application to populate this static data again into cache. So you need to think of how are you going to handle these static data if they got deleted based on your evicting data strategy. And also you want to make sure that you have a consistency between the application or the data store and the data stored in the cache. And definitely you can use a local or a memory caching for your application as well. Now, let's see when we should use this pattern. So when your application doesn't provide a native read-through or write-through operations, these kind of operations implemented in many caching systems at the moment. So you don't have to implement them unless you really have to. Also, when the resource demand is unpredictable, you can't tell exactly which user is going to access which resource and for how long. Again, we said this pattern is about accessing non-static data. It's not about the static one. When we shouldn't use this pattern when the cache data is static, as we just said, and also for caching session information. What we can use instead, you can use the sticky sessions that are available in the load balancer, which is going to be more efficient than storing them in the cache. All right, so over to you, Kasim, to finish it up. Thanks everybody for joining. Hope you enjoyed the session.